Morning, everyone.
What's happening? Somebody speak. Oh, recording stop join. But which way? There is no coming. I couldn't hear. Let's see.
Good morning, everyone. Welcome to our lecture. Um, I just want to make a couple of comments. I see we have 63 people. That's not good enough. Last week we had up to 80, I think, that people need to attend. I suspect that it's because I'm giving you videos that you can use that as a ruse to avoid attending the lecture. So I may not give you these videos in future, so I want to encourage you, and please do encourage everyone that they need to attend. There's absolutely no requirement or responsibility on my side to record these lectures and share the videos. I want you to understand that. Two, you'll probably have noticed that when you came in, you couldn't log in until I logged in. I've deactivated that because I had people logging in at weird hours, different days, late in the night. And you know, when you log in, I get some emails, and so I've deactivated that. You can only log in after I've logged in, but I'll try to log in on time and then give a few minutes for people to get into the lecture. Today I've given about 10, 12 minutes, and you can see we are still at 63 people. Now we're up to 67. So let's see how that goes. Now, we finished looking at registers. Today I want us to look at some MSI logic circuits. There are a number of these. MSI obviously is medium scale integration. So you have a number of these components on the same chip and you can use them. The thing is, with digital systems, we are always operating in some way. So this last lectures, the last chapter we've looked at are counters and registers. Those are operations. We are counting and we are storing things in registers and maybe pulling them out and so on. Some of the other applications that are within the MSI logic circuit range include decoding, and we are going to look at decoders today. Encoding, so usually when you decode, you also encode. Usually you first encode and then decode, but today we're going to start with decoding and then look at encoding later, because I think it's a little bit easier to understand decoding. We do multiplexing. I don't know if you know what multiplexing is, but we are going to be looking at this. And usually when we multiplex, we also demultiplex. These are things that are used within in all communication systems, but you know, every communication system has some digital signal processing and some digital electronics. So what we study here are components and applications that happen within actual systems. Some of the other applications include obviously counting, code conversion, some of the arithmetic things that you've looked at, storage, you know, how do we store data in memory? That includes registers, but those registers work with with some other applications. So like if you, we are going to have an opportunity in this lecture to talk a little bit about how memory works, but there's a whole other chapter that we are going to go to, I think, after this one and understand memory in detail. So today we want to start with encoding. Sorry, with decoding. Now, what does it mean to decode? Usually you have some set of information and you want to decode what that means. So for instance, I could have a certain code, CBA, and I have my decimal. Maybe you want to understand whatever this is in decimal. So you can say 000 in decimal, it is equivalent to 0. 001 in decimal, it's equivalent to 1, and maybe 111 in decimal, it is equivalent to to 7. Now, if I give you this kind of code and you convert it into that kind of thing that I can understand, which in this case is decimal, what you have done is you have decoded. You got a code and interpreted it in a way that some other application can understand. If we were moving in this direction, then we would be coding, and to code we use what we call an encoder. So these two go together, decode, encode. Usually we first encode and then decode. I could give you a number 9 and tell you to code it for me. It really means put it in some code that I can understand. And so if you're working with computers, if you have 9, you're going to have to decode it into some kind of binary code, for instance. This is coding. But if I have 1001 and I want to turn it into 9, I need to decode. Now, let us look at an idea. So you usually have a number of inputs and you get a number of outputs. These inputs could be 3 inputs, meaning that you have like CBA, but CBA can be either 0 or 1. So it really means that these will be combinations of, could be 0, 0, 0 all the way to 1, 1, 1. So CBA could be any input, but at the output here, usually you have 2 to the power n outputs. So if this is n is 3, that means you will have 8 outputs. And these are the 8 lines, 4, 5, 6, 7, and 8. Now, if for instance you have 0, 0, 0 this side, you want to activate one line on the output and all the others will be deactivated. If you look at that one line that is activated, you can easily tell what the output was. So for instance, depending on what I have here on the input, I can have a number of outputs here. Let me draw a simpler decoder so that we can understand. Let's look at a 2-input decoder, meaning I have A0, A1. As you can see, these are the n inputs. So just 2 inputs, and you can see that the inputs are active high. If I have 2 inputs, it means on my output I have 2 to the power 2, which is 4. 2, 3, 4. O3, O2, O1, and O0. Now, let's assume that A1, A0 is 0, 0. If A1, A0 here you have 0, 0, then you want to activate one output that corresponds to that combination on the input. So in this case, we could activate O0, okay? If A0 were, A1 was 0, 1, we want to activate O1. So that is O0, O1. And if we had a 1 here and a 1 here, we want to activate not 3. So to speak, A1, A0, and output, that means O3, O2, O1, O0. That means if I have 0, 0, 0, 1, 1, 0, 1, 1, I know that because my outputs are active high, it means that the activated output will be high, or the others will be low. That means I have a 1 here, and these 3 are 0. If I have 0, 1, I activate 0, 1 here, and the rest are 0, 1, 0. It means this is 1, the rest are 0, and 1, 1. This will be 1, and the rest are 0. Now, clearly, if depending on what input I have only one output activated, and that is decoding, because I know what that output corresponds to on the input side. If we were dealing with a 3-input code, if we look at this one, for instance, this is actually the circuit in detail, and this is the table. Now, this is a 3-input decoder. 3-input decoder. Now, because it's 3 inputs, outputs will be 2 to power n, which we said 8. Now, this is how we name decoders. We can say 3 line on the output, on the input, to 8 line on the output. You can see you have 3 inputs, 3 output line, 8 output lines. So we can say 3 line to 8 line decoder. We can also say 1 of 8 decoder. This 1 of 8 decoder means that only 1 of 8 output lines activated. Okay, so out of the 8 lines, 1 is active. That is why we say a 1 of 8 decoder. We can also say binary octo decoder, because you can see on the input we have binary, on the output we have 8 outputs, which is octo. Okay, so 8 is octo, and so this is really how we name decoders. So let us look at an example. This is a circuit. Let's say we have a CBA is equal to 0, 0, 0. If it's 0, 0, 0, we expect that we will activate output or not, but this is an AND gate. You can see that that's an AND gate, and so for this to be high, since it is active high, what is going into it should be 1, 1, and 1. So you can see that if A, B, C are both 0, we look at the lines going into this AND gate. One of them is that. And so if A is 0, that's a 1, meaning we have a 1 here. For this one, you look for B. This is the line. If B is 0, here it's 1, and so you have a 1 there. And if we come to C, we look at the other line. And if C is a 0 here, C is a 1 here, and that line 1 goes there. So we can see that that will be activated. If you do the logic analysis here, you realize that there is no other gate that will be active. So for instance, if we look at this one, if we look at gate 3, this line comes straight from here, because if this is a 0, you have a 0 here, and that's a 0, and so already we know that that is going to be a 0, meaning that only one of these outputs will be a high. Let us look at another example. If CBA is, say, 101, 101 is 4 plus that we expect O5, because that's decimal 5, we expect O5 to be activated, to be high. Let us try to see whether O5 will be high. C is 1, so let us look at the inputs going into 5. This input, the third input, you can see comes straight from C, meaning we have a 1 here. This line, the second line, comes from B. Okay, you can see that second line connects there. And from B, if B is a 0, then we have a 1 here going all the way to that. And the other one is 1. So A is 1. If we look at this line coming from A, it comes like that, goes all the way to that point. And you can see that if A is 1, then 1 comes there. And you're going to have a 1 here. And I can assure you that all the others will be 0. So this is how we decode. Based on what we have at the input, we activate one line at the output, and all the others will be deactivated. And that line that is activated helps us to decode the combination at the input. If some of you were paying attention last week, we did some decoder circuits for the Johnson counter and for the normal counter, the normal binary counter. We did some decoding circuits. That time, the values were coming straight out of the flip-flops, and we were able to decode them to know what the state of the counter is at that time, at that count. But in this case, A, B, C might, for example, come from counters. It might come from a memory, like a register. It might come from any other part of the digital circuit. It doesn't always have to come from the counter flip-flops and so on. And so you can see that for each combination of these, you only have one line active, okay, in each combination. This table could be written as, could be drawn as this. I wouldn't have a problem. Outputs, you could say 07 to or not, for instance, 000, 001, 010, and so on to 111. And here I would have active output. I am only interested in the active output, 01, 02, all the way to 07, so that you don't have to draw this whole thing. Okay. If you have any questions, please put them in the chat. I see some people are asking that they want videos. As I've already mentioned, I am not obligated to give you those videos. Okay, I'm happy to give them to you, but if people start dodging the class in large numbers, then I will be forced not to give those videos. I think for me it's simple. If you take this seriously, then of course. But if you don't, then I'm not obligated to help you along. Perhaps there's a reason why you don't care. Right. Let us look at another idea of enable inputs. Now, enable inputs are not, it is not the first instance we are looking at an enable input. An enable input usually is used to enable or disable the operation. So in this case, we can enable this decoder to work or disable it completely. And so we have an enable input. And in this case, the enable input could work like this. We have one line. I don't know where to pass that line. Let me pass it here. That is going into all of these. Okay. So this each AND gate now has a fourth input, and so we have 4 input NAND gate. Now, depending on what we have at E, it will disable the decoder, and the other obviously will enable the decoder. So if E, okay, we can have E and decoder operation. So obviously E can be a 0 or a 1. Now my question is, what is the value of E that disables the operation, and what? When, okay, so for example, when E is 0, what do we get? Is the decoder disabled or enabled? Okay, thanks, Livia. So this is going to be disabled, because you can see that if E is a 0 and the 0 is going into all these AND gates, then all of them will always be 0. Okay. However, if it is a 1, and then the gate which was to be activated will still be activated, since this enable input is high, it cannot stop. It cannot force the AND gate to give a 0. And all the other AND gates that we are going to return a 0 will still return a 0, because this one cannot force them to return a high if they have other 0 inputs. Okay, so that is a disable. And so if E is 1, we are going to have an enable circuit. And so for this type of decoder, you can have a simple enable input that is a high going into all the AND gates. And that will give you the ability to either enable or disable. You can disable if you put that input to 0. You can enable when you put that input to a 1. Okay, thank you. Let us look at another decoder that uses enable inputs. This decoder, I'm surprised that right, let's continue. This decoder has an enable circuit. This is an enable circuit. You can see that that enable circuit is an AND gate. So you have an AND gate that has 3 inputs. 2 of them are active low. And so you can have E1 active low, E2 active low, and E3, which is active high. So for you to get an output that is high here, this is your enable input, as you can see. This enable input out here goes into all the AND gates, as we have just said. For us, what we want is E high. We want an E, a high E, you know, like the output is high, so that that high goes into the AND gates for us to be able to activate the decoder operation. But this is only going to happen when E1 is equal to E2 is equal to 0 and E3 is equal to 1. I think that is quite clear. And you can already see in this table that if E1 is a 0 and E2 is also a 0 but E3 is a 1, then we will respond to the inputs. These are the inputs of the decoder. The decoder is going to work as we expect. But any other scenario, the decoder will not work. And so if E1 is a 1, we don't care what the others are. We know that the AND gate will produce a 0, and that 0 will, sorry, the AND gate, they enable this AND gate will produce a 0, and that 0 will make everything 0. I think you can interpret all the other active. I don't know who is writing. I'm quite surprised that people are writing in my. If you are writing in my notes, please desist. I need to figure out how to stop it. I didn't know that that was even possible. Somebody is writing in my screen. Let me see. Is that even possible? It's not. Okay, I don't know what just happened, but please. So I should go to the clipboard and disable. Okay. Thanks, Arvin. Yeah. Yeah, I'll deal with that in later. Let's continue, but please desist from typing on the clipboard. Now, once we are in this state, then we can start operating. This circuit, detailed circuit, is actually corresponding to the 74138 1 of 8 decoder, meaning that you have 3 inputs and 8 outputs. And so if, for instance, let us look at an example. If I had A2, A1, A0 as 0, 0, 0, I'm looking at 0, 0, 0. I can see that the first one comes from here. Okay, so if this is 0, that becomes a 1 going into there. The next one is there. All right, the next input. So if that's a 0, this is a 1 coming into that. And the other one is that from that point. If this is a 1, if this is a 0, then that's a 1 coming into there. And so if my enable circuit, the fourth one is high, then I'll get, if this is, then I'll get a 0. Now the difference with this is that these are active low inputs. Active low means that all the other inputs will be low. Sorry, all the other inputs will be high except the activated output. So when the output is activated, it will be in the low state. This is a 74ELE3103, which is a 1 of 8 or a binary 2 octo decoder. If, for instance, this was 0, 0, 1, which means that our decoder is activated, and I have 1, 0, 1, then I'm going to be activating, I think that is O5 will be 0, all the others will be high. Okay. Let us carry on. We have our 74 ALS 138, we can combine a number of them to produce large decoders, okay? Combine ICs to create larger decoders, right? Now we can see here that we are combining 4 of them. Since each is 1 of 8, if we combine 4 of them, we are going to get one of 32 decoder. Now, if you notice here, we need a way, you know, 1 of 8 will still be our original 3 inputs, but we need a way to differentiate between which one we are selecting. So we need we can use our enable inputs to activate only one IC at a time, obviously corresponding IC depending on what we are doing. If we are doing 1 of 32, it means we start at 0, 0, 0, 0, 0 to 1, 1, and then 1, 1, 1. So it means that this can be A4, A3, A2, A1, A0. Now we use A4, A3 to select a decoder, an individual decoder. And then obviously A2, A1, A0 are our inputs. And so we can use these ones to select which decoder we are going to be using to decode. If we are in the range, for example, let me get a new slide. Right, let us look at an example like this one. If we have 0, 0 to 0, 0, 0 up to 0, 0, 1, 1, 1, if you know these are 8. These are 8 combinations. We are going to be using the first one. This is the first one. First, second, third, and fourth. We are going to use the first one, and this is Z1. That's what they've called it, Z1. And our outputs will be in the range 0 to 07 active low. Now the next point here, the next step should be 0, 1, again 0, 0, 0, all the way to 0, 1, 1, 1, 1. These are also 8 combinations. And then we activate Z2, which is now, instead of 0, we can rename it to 08, all the way to output 15. The next one is, the next point here, obviously the next step is 1, 0, 0, 0, 0, all the way to 1, 0, 1, 1, 1. These are another 8 combinations. There we need to activate Z3. Our output should be 016 to 023. Okay, and then the next step here is 1, 1, 0, 0, 0, all the way to 1, 1, 1, 1, 1. These are also 8 combinations. We activate Z4, which is 024 to 031. Now, if we start from 0 to 031, we can see that those are 32 inputs, which gives us 1 of 32 decoder. Let me see what's in the chat. Tom, what do you mean I'm too fast? Do you have any question, please? If you have any questions, please ask. But I'm not very sure if I'm too fast. Maybe because you know these things, you really need to go back and sit down and try to understand them on your own. You know, looking at all these circuits, to understand what they really mean. I may not be able to go through every little thing, but I'm trying to set this up so that it's clear to everyone. And so using our F4, you can see that our F4 could be 0, 0, sorry, F4, A3. If it is 0, 0, we activate Z1. If it is 0, 1, we activate Z2. If it's 1, 0, we activate Z3. If it's 1, 1, we activate Z4. So let us go back here and see. A4, A3. If it is 00, Z1. If it's 01, Z2. If it's 10, Z3. And if it's 11, Z4. So you can use this to activate these individual decoders. So for instance, let us look at the case of Z1. We want A0, we want A4, A3 to be 00. What we have done here is to make A4, A3 to go into these inputs. These E1 and E2 are active. E1, E2 are both active low. That means that if this is 0 and that is 0, and we have held the active high input to a high, then this will be activated. However, for the case of this one, if we have a 00, if we have a 00 here, already we can see that that is 0, that is a 0 also, but this one is connected to a 0. So it will not be activated. If we still have a 00 here, once again, we can see that F4 will be 0, meaning that that one is not activated. And on this side, if F4 is a 0, once again, that line is not going to be activated. So when we have a 00, only Z1 we can clearly see will be activated. Let's see. Let us look at another example. What if A4, A3 was a 1 and a 0? If F4 is a 1 and that's a 0, we expect that Z3 will be activated. Let us try to prove that. But before we do that, 1 of 8. Explain more about the meaning of 1 of 8. 1 of 8, 1 of 8 is really simple. You can see that we have, let me go back and get this. Okay. What do we mean by 1 of 8 decoder? 1 of 8 decoder. You can see that it has 8 outputs. But if we are decoding, depending on what we have here, only one of these will be activated. So for instance, if we have 000, only that will be activated. If we have 111, only 07 will be activated. In this case, because the outputs are active low, activation means that it is out, it's low, all the others are high. So because only 1 of 8 outputs is activated, we call this a 1 of 8 decoder. The one I've just been working on is a 1 of 32 decoder. We can also call it a 3-line to 8-line decoder. You can see these inputs are 3 lines, outputs are, so it is the number of input lines to the number of output lines decoder. Okay. Does that mean that the state of A 0 to 2 doesn't matter in the enabling process? Oh, it does. No. In the enabling process, so A0 to A2, Namwanja, A0 to A2 are the inputs. A3 and A4 are the ones that we are using to enable the circuit. And so A0 to A2, it doesn't mean, or A2, A1, A0, it doesn't mean that they don't matter, but actually those are the inputs into the decoder. But we are using A3 and A4 to choose which of the individual decoders to either enable, and the others would obviously then be disabled. I'm going to, let me first complete the explanation of this, and if you have any questions, you can ask. Okay, so we see that we have a 1 and a 0, A3 and A4. We want to prove that Z3 will be activated. Let's start with this Z1. Z1, because that's a 0, that's fine. But in the next one, A4 going into E2 will disable that line. meaning that that's disabled. If we come here, we see that E1 is a 0. That's okay because it's connected to ground. E2 is 1. Sorry, E2 is 0, is 1. Already, we know that that is deactivated, but also the third one would actually be deactivated because that's a 0 going into an active high input. Let's look at Z3. We have a 0, so that's fine. We have a 0 coming from A3 going into E2, that's good. And we have A4, a high going into E3, that's also good, meaning that that is activated. And we can see that that's, because that's a 0, on here it's a 1, and if it's a 1 going into a 0, we know already that that will be deactivated. That's okay, and that's okay, but that's deactivated, meaning that only this is active. Now, if our A0, A1, and A2 was, for example, 1, 0, 1, 1, 0, 1 would be like the fifth, you know, it's like 5. So we would be having O5. But remember, we have renamed these. So it's actually just like O0, O1, O2, O3, O4, O5. So if our output is 1, 0, if our input A2, A1, A0 is 1, 0, 1, we are going to have this activated. This line is O, if this is 23, 22, is output 21 will be activated. Okay, so that means that if our input A4, A3, A2, A1, A0 is 1, 0, 1, 0, 1, then we activate O21. O21 will be activated. All the others will be deactivated. Why are the outputs active low? It's the design. I really don't, I can't, you know, that's it. That's the way it is. We've seen so many cases where some outputs are active high, other outputs active low. And if you go back to the third or fourth chapter, I believe it's the fourth chapter, you can see why sometimes we change outputs into active low or active high, depending on what they are driving, what is behind it. Remember, there's a time in chapter 4, I believe, where we studied that when you have a bubble in output, it should feed into a bubble input. And so sometimes these things become active low, active high, depending on what they are driving further forward into the circuit. If you don't remember things in chapter 3, chapter 4, please, you need to go back and do it. Yeah, this is active low. This is an active low output clearly. If we have our A4, A3 as 1, 1, we expect to select that, and we can see that if it, for instance, 1, 1 here, 1 will become a 0 here, meaning that that's fine. That's already fine because it's active low and it's grounded, and the 1 going into there, meaning we select Z4. Now, if our A2, A1, A0 was 0, 0, 0, for instance, meaning that we have 1, 1, 0, 0, 0, we expect to select 0, output 24. So that's activated, and we have 0, 0 coming in, meaning that they will activate O24. Okay. Right. Let's see if I have. So really, that is the explanation of this, and so we can Okay, sorry about that. I'm going to have to repeat everything that I've said. Hopefully you can hear me now. Let's see. Yeah, sometimes in Makere, internet just goes off. And when it does, you know, everything shuts down. But I always have an alternative source. Which comes first? Is it the enable bits? It is the enable bits. I was usually, if we have our inputs as A2, A1, A0, and we are going to combine a number of these to create one decoder, then we should add our inputs, the enable inputs on the most significant bit side. So that's why we had A4, A3. Now, the reason why we added these was so that we have a total combination of 5 inputs, because we know that 2 to the power 5 is 32, and so we can have unique outputs corresponding to a combination of 5 of these. However, we retain our inputs as those, and we use the extra ones to enable or disable, basically to select the decoder that we are using. Now, what if I was creating a 1 of 16 decoder? If this is the case, I only need A3, A2, A1, A0, which are 4 bits, because 2 to the power 4 is 16. And so then I would have A2, A1, A0, and then I have my A3, and this A3 is either a 0 or a 1. So if I have my 2 decoders side by side, I can have, I don't know how you want to do this, you can design this, but I can have A3, and if A3 is 0, I enable this. If A3 is a 1, I enable that one. So what I'm going to do is to leave you with this. I want you to create for me, you know, you don't have to show me, just do it. I'm going to take a break. I want you to create for me a 1 of 16 decoder, and please combine 2 of these decoders to create a 1 of 16 decoder. We are going to have just 5 minutes because we missed time at the beginning. We are going to have just 5 minutes and continue. Please draw these side by side and see how you would connect them. I'll be back in a moment. 5 minutes. Okay, thank you. I'm back. Let's see. Unfortunately, you cannot share. I can't allow you to share. Um, there used to be incidents of people sharing funny things, so I always disable sharing. But if you have something like this and something like that, so for instance, and obviously you have your A4, A3, and A2. The best way to, I already said that if you have a one of 16, you can only have A3, A2, A1, A0. You can have another input, but it will be wasted because this is enough to resolve all of the whole decoder. So this is either a 0 or a 1, and this 0 or 1 is used to choose whichever of these two. For example, that's Z1 and Z2. And if this is Z1 to Z2, we can, for instance, say that let O0 start here towards O7 here, and then here we would start with O8 going all the way to O output 15. Okay, again, active low. And we can, if for instance we want, we can connect this to the ground, and we can connect that one also to the ground. That means that both of them are always activated. They are always in their active states because they are active low and we've grounded them. That means we are going to use E3 to activate one or the other. Now I could have my line A3, okay, and I say that for instance I can say that let this go in there, and for this one it will connect straight there, right? And then obviously I have my A0, A1, A2. These are, on both sides. Those are available on both decoders. That means that if A3 is equal to 0, okay, which is this case, you have a 0 here. If it goes there, it will deactivate this. If it goes in here, it is converted to 1 and it will activate Z1. So we activate Z1, meaning that, okay, Z1, meaning that now the Z1 can respond to inputs A2, A1, A0. If A3 is a 1, 1 coming in here, meaning if this is a 1 instead, this becomes a 0, deactivating that, but a 1 will activate that, meaning that I've activated A2, Z2, sorry, which can now correspond or respond to the inputs. And so in my table A3, A2, A1, A0, I will have obviously 0 and the rest 0, 0, 2, 1, no, to 0, 1, 1, 1, and this corresponds to Z1. Then the next point stage here is 1, 0, 0, 0 to 1, 1, 1, 1. This will correspond to Z2. And my outputs here would obviously be from O0 to O7. And this would be from O8 to O16, which gives me my decoder. Now, I think somebody, Namwanji or somebody asked how we can decode this. Remember in here, each of these has, I think this is an AND gate. Remember we had this, yeah. So here you have these NAND gates. And the best way to decode it, we've already seen. If you, for instance, NAND gates, how do we disable NAND gates? You need to look at how NAND gates behave, 0001, 1011, meaning that you're going to have out NAND gate outputs. This is a 0, the rest will be 1. So for us to disable this, we need to add another input, and if that input is a 1, then we have enabled. If it is a 0, we have disabled. So to speak, if we don't want to disable using that, because you see with these ones, we cannot really disable this circuit because depending on what F4 and whatever is, it is always enabled. Another thing we could do, for instance, no, in this case, we cannot do that. But what I was going to say is that we can disable our things, like we have another input that goes into all of these to disable them. If we want to disable the whole thing, we just get one input, feed into all of the AND gates in all of these, and we will have an issue. The other thing is that instead of having F4, F3, now we would have another F5. But how can it go into this? Perhaps what we can do is relook at the design of this and see if it is possible to use just F3, F4 to disable these, or F5, F4, F3 can be you can reconnect it across these four decoders to see if it is possible to disable the whole thing. Please have a look at that and see. Okay. Let's see. I think James Odongo. James, actually, I do put these videos on my Google Drive and I share the link. I understand that network is a problem, but I think you are putting this on me. This is not on me. Even me, I'm suffer because of network, because I'm not supposed to provide myself network. I insist that much as you want these videos and I can provide them, people must attend. Okay, so it's a deal, really. You want the videos, as many of you as possible must attend the live lectures. Otherwise, I might as well sit at home during the weekend when I have time and just do a video without anybody in class, and I give it to you. I mean, this is, to me, would be the same for people to dodge the classroom and just wait for the video. So once again, I insist that I'm not obligated to give you videos. It's a deal. You attend, you get the videos. As simple as that. Ian is asking, is it possible to have an input going directly into the enable side without an AND or NAND gate for this particular case? Where the enable, the AND, I don't know if I get your question, but the enable input, the enable inputs are 3 here, and this is by design. We really cannot add another input there because the AND gate is a 3 input AND gate. But I believe with digital circuits, there is a way you can always figure out how to redesign things and how to reconnect them to get what you want. So this is a challenge for you that I don't want to answer right now. You can go and do this and see if it is possible to do. How do we know that a decoder will have 1 enable input or 2 enable inputs? In fact, this decoder has 3 enable inputs. E1, which is active low, E2, which is active low, and E3, which is active high. But usually decoders are different, and so if I give you a decoder, I will give you all the information you need to be able to execute. So for instance, the first decoder that we looked at, which was this decoder, as you can see, it does not have an enable input. Okay, it's just inputs and outputs, whereas this one has an enable input. I don't know why. Yes, or this one. By the way, I need to tell you that if you buy this, you will not see that. You will only see it will be in a substrate like that. You will not see that this AND gate is not outside. It is really inside here, but it is put on the outside of the IC for clarity. But it is embedded within the substrate. You only access the inputs. All right. Let us now look at the BCD to decimal decoders. BCD is binary to decimal decoders. Decimal is 0 to 9, so 10 outputs. Now, what it really means is that now we have a special decoder that only works or only has 10 outputs, okay, instead of 16, because we see for the other ones, if we have 4 input or 4 line, it will be to 16 line. And I think we saw that where? I think here. You can see that we did that. We have 4 inputs and we have 16 outputs. But in this case, we are going to have a 4-line to 10-line decoder. This is so-called BCD to decimal decoder. It only decodes the decimal outputs from 0 to 9. Your 4 inputs, we know that these will range from 0000 to 1001, which is decimal 9. And the output, this usually is arranged in such a way that if you feed into here something that is not within that range, so for instance 1100, you should not get an output. The whole thing should act as if it is disabled. That can be within that. This is the detailed circuit. As you can see, quite complicated looking at the lines and everything, and I will not dwell on it. But this particular BCD to decimal decoder is a 7442, which is active low outputs. It has active low outputs. And so if you have 0000, you're going to have O0. And if you have 1001, you are going to have O9. And that's where it stops. That's its range. You can see its inputs here and the active output there. I think I mentioned this earlier when I said that this truth table does not have to look like that. You don't have to draw the whole thing. You can just give me the active output for a specific combination of inputs. So 000001010 all the way to that. This is what your decoder decodes. Okay, you feed it with a certain combination of inputs, which are binary values. It outputs one active line, which is active low, meaning all the others would be high. And that active low output corresponds to the input that we have fed it with. Now we want to look at some applications, and these applications are not very difficult, but usually we said that you have these values, the inputs are coming, usually they are coming from a counter. And that's why we use the decoders to decode the output of a counter. Okay, so usually they are coming from a counter. They can also come from a register. These are inputs can come from any other place within the digital circuit. But one application of this is that we can use a decoder to decode what is at the input and maybe produce light or generate a clock signal. We can do a number of things using the output of the decoder. Let us look at this application, which employs a counter actually. BCD to decimal, BCD to decimal, BCD to decimal again. That's fine. Just briefly for you, BCD to decimal. Okay, I'd say that for this one, we really don't need to look at the detailed circuit, but you can in your free time just to prove to yourselves. Yeah, so BCD is binary coded, decimal to decimal. We know that we have 10 digits in decimal. That's from 0 to 9. And we know the corresponding values in the binary coded decimal. This would be 000 to 1001. And so we have our 4 inputs because clearly a binary coded decimal has 4 digits. And at the output, each binary code will correspond to a certain decimal input. If this is activated, that's 9, 8, and so on. That's 0, that's 1, and everything in between. And this is the truth table. When we have our inputs as 0, 0, 0, we should activate the first output. 0, 0, 1, 0, 1, this is O1, that one, and so on and so forth. And for this part, where these are codes, they are binary 4-bit codes that do not correspond or are not part of the binary coded decimals. If you were to have this input here, so say for instance 1111, everything output here should be high or should be high because that is the inactive state. It shouldn't show an active state because it does not correspond to anything that we expect. Otherwise, It is just as normal as any other decoder. It's just that its outputs are 10 instead of 16, yeah, because of the whereas it has 4 inputs, and we can say 1 of 10 decoder. We can say BCD to decimal decoder. We can say 4 line to 10 line. People are still writing on my screen. I don't know why they keep doing that. Please, if you are doing, is it Godfrey or somebody? If you are doing that, desist, because you continue to do it. And actually, somebody gave me directions of how to change it, how to stop you, but I couldn't figure it out. One example of BCD to decimal. Okay, fine. What is the activated output? Output when BCD, when DCBA of a 1 of 10 decoder is equal to 0110. Okay, what is the activated output? So the BCD to decimal decoder is not any special. It's just that its inputs are 4, its outputs are fewer. Okay. Thanks, Alvin. I've done that. Hopefully now nobody will be disturbing anymore.